All right. Before we finish up what we needed to finish up last time and before we jump into the new stuff, let's spend a little bit of time and go over the rules that we talked about last time in terms of naming alkanes. Where do we start in naming alkanes? What are the three things that we've got to do? What do we start with? We find the longest continuous chain, right? That's the first rule. We're always going to, when we look at a molecule, we're going to look for that longest continuous chain. I think finding the longest continuous chain works better if you're talking about the bond line drawings, okay? Not the condensed structure. So if you're given a condensed structure like you were at the end of class last time when we all worked together, I would convert that into a bond line drawing. So once we identify the longest chain, what do we do to that longest chain?
Number it.
Circle it. Well, we're going to number it. You're right, but I would circle it, and then we're going to have to figure out a numbering system, right? So you're absolutely right. We have to figure out a numbering system. Then what do we have to do?
Decide what side we're going to start counting.
Okay, yeah, in terms of the numbering system, whether we're going to go from left to right or right to left or up and down and side to zig, however we're going to go, right? Got to figure that out. Then we got to figure out what's outside that circle, right? And those are substituents. For the purposes of this chapter, they're all alkyl groups, right? So let's look at the one over here on the right. Okay, so what is the first thing that I need to do? Yeah, I got to identify it and circle it, right? So let's see, 1, 2, 3, 4. Nah. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Maybe, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. Now, it looks like 9 is going to be the longest chain, right? So I'm going to circle that. Okay? And I'm going to circle it in purple. Whoop. Almost made a faux pas. There we go. Right? 9 carbons. What is the parent name going to be? No name, right? So this is going to be something, 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 no name. Okay? Now I've got to deal with a numbering system, right? I can either number from left to right, 1, 2, 3, 4, 5, 6, 7, 8, 9, or we'll call that the purple numbering system. Or I can do 1, 2, 3, 4, 5, 6, 7, 8, 9. Are we going to go with the purple numbering or the green numbering? And why? Yeah, so if I go on the purple route, I come to my first point of branching at carbon number 3. If I go right to left, I get to my first substituent in the green numbering system at carbon number 4, right? 3 comes before 4 on the number line, right? So that's what we're gonna do. So I'm gonna erase the green numbering. Okay. Now what do I have to do? I have to identify what these substituents are, right? Well, this is a CH3, so what's that called? That's a CH3, so what do we call that alkyl group? Somebody said it. It's not an aldehyde, that's a functional group. Methyl. It's 1 carbon. It looks like methane minus a hydrogen. So it's a methyl group, right? So this is a methyl group. I also have a CH3 here, so that's another methyl group. What about this group? Well, how many carbons does it have? It's got these 2 carbons with 3 hydrogens, and it's got this carbon with another hydrogen on it. So how many carbons is that? 3, and 3 is what? Prop, right? Propyl. But wait a second. Propyl would be if these carbons were here, here, and here, right? This is in the middle carbon. This is called isopropyl. Iso meaning isomer, the isomer of propane. So it's on the number 2 carbon of the 3, right? If I was counting these out. So I have an isopropyl group and I have 2 methyl groups. So how am I going to name it? It's going to be a dimethyl isopropyl nonane, right? So I've got methyl groups on carbons 3 and 4. So it's going to be 3, comma, 4 dash. Why the dash? Dash between numbers and letters. Dimethyl dash. What comes next? Just the isopropyl? I got to have a number, right? So what's the number? 6 dash that is the name of that hydrocarbon. Yes, ma'am.
Isopropyl is up first with good.
But it's propyl. So we don't usually base it on those little prefixes like that. Okay, so that's the name for this particular molecule. Now let's look at this one. Okay, a little smaller molecule. The first thing that we've got to do is what? We got to find the longest continuous chain. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Looks like 6 is going to be the longest chain. So I'm going to circle it again in purple. And what do you just recognize?
There's 2 of them.
All of the substituents are now methyl groups, right? But didn't that kind of look like an isopropyl group when you just looked at it? It's not a substituent, right? It's part of the longest chain now. This wasn't part of the longest chain, so it became a substituent, right? So there's not going to be any isopropyl in this. And so we have a CH3 here, we have a CH3 here, we have a CH3 here, so we're going to have a trimethyl, right? So now we've got to figure out numbering, right? So if I go from left to right, 1, 2, 3, 4, 5, 6, or if I have my green, move my green. What did I do with it? How can I lose that fast? I don't know. Or I could go 1, 2, 3, 4, 5, 6. Which way am I going to go? Right to left or left to right? If I go right to left, I come to the first branch at carbon 2, right? If I start left to right, I also come to carbon 2. I can't make a decision there, right? So I got to look at the next substituent. The next substituent comes at carbon 3. The second substituent going this way would come at carbon 4, right? So we're going to go left to right. Okay, so 6 carbons, it's going to be a hexane parent. And it's going to be trimethyl. So it's trimethylhexane. Now what do I have to put in? Got to put in some numbers, right? So it's going to be 2, 3, 5 trimethyl hexane. 2, 3, 5 trimethyl hexane is going to be the appropriate name for that particular molecule. That just bugs the living daylights. Oh, there it is. Silly me, silly me.
Can you make the computer?
Yeah, I can try. That help?
Yeah.
All right. So that's where we kind of ended off. We can also have hydrocarbons that have rings. Are these hydrocarbons saturated or unsaturated? Unsaturated. Remember, an unsaturation can be a ring or a double bond, right? So these are unsaturated. This particular one happens to have 6 carbons in the ring, okay? And so cycloalkanes are typically named using similar rules, but the prefix cyclo immediately precedes the name of the parent. So you're going to find the prefix, you're going to add cyclo, then you're going to add parent, then you're going to add suffix, okay? So if we find the parent cycloalkane, what do we have here? 6 carbons in that ring, right? So it's going to be cyclohexane. Okay, it's going to be a cyclohexane parent. Now in this class, you'll immediately know whether it's got to be a cyclo compound or a regular alkane. I'm not going to do the stuff where you have to figure out whether or not the cyclic part is a substituent or not. Okay? We're going to keep it pretty simple. So we've got 6 carbons in the ring, so we've got cyclohexane. What are the substituents then? The ring itself is the parent. What's hanging off the ring?
There's a methyl group.
We've got a methyl group and we've got 2 carbons. Ethyl. Right, so we've got a methyl group and an ethyl group. So this is some type of ethyl methyl cyclohexane. What do we need to do now? We need to number that particular set of rings. Okay? So we can figure out whether or not we're going to number from clockwise or counterclockwise. How do you think we want to number? We want a number to give everything the lowest possible number, right? So in this particular case, we're talking about dimethyl cyclohexane. They switched it up on us, okay? But if I number clockwise, my groups would be on carbons 1 and 3. If I number counterclockwise, they would be on 1 and 5. So I want it to be 1,3 dimethyl cyclohexane. Same rules still apply, okay? Now you can have a situation where you only have one substituent. You don't need to number. I don't need to say 1-methyl cyclohexane. Why? Because no matter which carbon I put that methyl group on, it's always number 1. Okay, it always gives you the same compound. Same thing over here for this cyclopentane. That group that's hanging off of it is a butyl group, but it looks like a T, so we call that tert-butyl. Everybody see that? How that kind of looks like a T? Hanging off that cyclohexane ring? It's called tert-butyl. Okay, so that is tert-butyl cyclohexane. We do not have to call it 1 tert-butyl. Okay? But if we have 2 substituents, 3 substituents, so on and so forth, we have to identify their location. So let's look at some examples. Just on paper. So get in your groups. Name that molecule. what should we do here? What's the first thing that we do? Pardon? Do we number? Is that the first thing we do? We identify the ring, right? So what is it here? Hexane. So it's a cyclohexane, right? Because it's cyclic. So this is going to be something cyclohexane. And so all of these things that are hanging off of that ring are substituents. Okay? So now we got to figure out numbers. And we want to do this in a way that gives us the lowest possible number for all of our substituents, right? So that's going to tell us where we need to start. We could start at the top and go clockwise, which would be 1, 2, 3, 4, 5, 6. And that would give me 1, 1, 4 trimethyl, 3-ethyl. That's one way to number it. We could also number it counterclockwise, which would give me 1, 1, 4, 5. That doesn't seem like that's going to work, right? Okay, so, but we could also start numbering here, right? So we could start maybe numbering here and figuring out. So we could go 1, 2, 3, 4, 5, 6. We want the lowest possible number. So which one do you think is going to work? Think the last one's going to work? So that would give us 2-ethyl, 1,4,4 trimethyl cyclohexane. Is that going to be the lowest possible numbering? Let's try this one, this numbering system. So that would give us 3-ethyl, 1, 1, 4 trimethyl cyclohexane. You get complicated, can't it? So what do we do in this case? I would have gone with this numbering system. Lowest location numbers for the most substituents. Okay. All right. Yeah.
I think I may have missed something. How are you getting 1,1,4 for the trimethyl?
So there's a methyl here that's on carbon 1, and this methyl is also on carbon 1. That's where the 1, 1 comes from.
Okay, well, why did we add the 4?
Because there's a 1, 2, 3, there's another methyl
okay,
here.
Okay.
Yeah. Does that make sense?
Yep.
Okay, good. Let's jump into what we need to talk about today. We're going to play with our models quite a bit today. So go ahead and get those out if you got them. So today we're going to talk about rotation around single bonds. Single bonds are also called sigma bonds. We're going to talk about this thing called Newman projections, and we're going to introduce you to something called conformational analysis. Okay? So if you take a couple of carbons and put them together, and I'm just going to use some white spheres as well, right? So here we have methane, 1 carbon, 4 hydrogens. When I put these two together, now what do I have? 2 carbons is called what? Ethane, yeah. Or if it was a substituent, ethyl, that's right. And I'm just going to randomly put 2 white spheres on my models, one on each carbon atom. Something like that. Is that the same as that? No. I can rotate around single bonds. Your model does this very well. And in fact, at room temperature, this molecule, if it really existed, would be, these atoms are spinning and vibrating and moving all the time. Okay? So it could, you know, these two hydrogens, or these two white spheres could be really close to one another, or they could be really far apart from one another. Okay? Do you think they want to be close to each other or far apart from each other? They want to be far apart. Pardon? Well, things that are same charge certainly want to be far apart, but these are neutral. But it's kind of like your personal space, right? You've got your personal space, you don't want people invading it, right? So molecules behave the same way. Things that are similar want to be far apart from one another in the structure. And if the bond can rotate, it will, okay? This is called conformational analysis. When we can rotate around single bonds, this is a different conformer than this. The structure hasn't changed in terms of how it's named. It would still be dihwhite sphere ethane, if I was to name it right now. 1,2 dihwhite sphere ethane, to be more precise. Okay? But there are different conformers. There's this conformer, there's this conformer. There's an infinite number, right? We can do all this. Okay? And so we're going to talk about how we look at these types of conformations today and these rotations around sigma bonds because it's very important. This is why polymers take on shapes. This is why biomolecules take on shapes, because these bonds can be rotated around. They can be moved. Okay? And so we just built a model of an alkane. These two white spheres, alkane, right? You know that. Now let's build what's called an alkene. So you need, to build an alkene, you need two gray pieces. And you need this double bond piece. And you take the gray piece and you stick it inside and you pop it. Stick it inside the double bond and you pop it. Now we have ethene. It's an alkene. We haven't talked about alkenes yet. But it has a pi bond. And that's what this double bonded piece means. You've got a sigma bond in between it and a pi bond from the two p orbitals. Okay? Now I'm going to stick two white spheres on it. One on each carbon. Doesn't matter how you put them on. Okay? So I've got this. Can I rotate around these two carbons like I did on the other one? Try it with your model kit. It's not going to let you. I mean, yes, I could say enforce it and do that, but I'm breaking my model kit doing that. It doesn't want it. Okay? I cannot rotate around a carbon-carbon double bond like I can a carbon-carbon single bond. Okay? And so these two white spheres will always be like this. Now you could have built it to where they were like this, and that would have been perfectly fine. But they will always be like that. You can't rotate around them. Okay? These are more rigid. Okay? These little things appear in polyunsaturated fatty acids. It's why polyunsaturated fatty acids have the shape that they have. They're also responsible for why polyunsaturated fatty acids go rancid and oxidize and make goo and clog up your arteries. Okay, it's these little double bonds. Okay? They limit what can happen. You've probably heard of cis and trans fats. We'll talk about that. Those are different conformations around an alkene. Okay? But the model tells me I can't rotate around that carbon-carbon double bond. It's fixed. These things are fixed in space. Okay? And that's very, very important for the chemistry that we'll be talking about later on. Okay? So, as I've just mentioned to you, rotation around a single bond, we call that conformer. So we have a conformer on this side, we have a conformer on that side, right? So you just rotate around the single bonds. And there's enough energy at room temperature for single bonds to be rotating all the time. Okay, we have a magic microscope that we can go up. It's not really a microscope, but it's kind of magic. You can go up and you can see these molecules through a process called NMR, which we'll learn about later. And at room temperature, you can actually visibly see that these things are rotating. And you can cool them down to really cold temperatures, and you can start to slow that rotation down. So that we know that this really happens through the experiments that we can do, okay? Now, you have to be able to represent conformations on a two-dimensional space. The board, your paper, your exam. You have to be able to represent conformations to do conformational analysis. And this turns out to be what we call Newman projections. I take a three-dimensional object and I'm going to project it onto a two-dimensional surface. What is this like in your everyday life? On a sunny day, which we haven't had all week, if you're walking out on campus, what do you see following you? Your shadow. Is it three-dimensional? It is a two-dimensional projection of your three-dimensional self on a two-dimensional surface. That's what I'm talking about doing with this. Okay, so what you can do one day when it's nice and sunny outside, build your model. Go outside and hold it up when it's noon so it'll be right above. And what you will see is a projection of your model onto a two-dimensional surface. Okay? That's what Newman projections are. Okay? So imagine taking your model, putting it up here, and then just smashing it into the board. But you'll notice that to do that, I have to hold a bond to do that, right? So I'm taking this bond and I'm smashing it into the two-dimensional surface. So a Newman projection is always looking down a carbon-carbon bond. So you will hold the bond and you will look down that bond and you will see the Newman projection. Okay? Now, as I'm holding this, this is going to be, let me change the color. Let's make this one red. And let's say that the red and the white are 180 degrees apart. I'm holding this molecule and I'm looking at it. That's the Newman projection. How do I represent that on paper, though? Well, what I have to do is I have to represent the carbon in the back, the one that's away from me. And I represent that by a circle. But I also have the carbon that's closest to me, right? I'm going to represent that as a dot. Okay? And what I see attached to the circle going straight up is the red and then these two sticks. Just like that. Everybody see that? That's what's attached to that back carbon. What's attached to the front carbon? Two sticks and a white ball. That is the Newman projection for this. And you can clearly see that the red and the white are 180 degrees from one another. Okay? That's that Newman projection. This carbon atom is bound to the back carbon atom, but you don't see that bond because you're looking down it. So we don't represent it with anything. This is a bond to only whatever is out here. It is not bound to that back carbon. Yes, it crosses through it, but it doesn't bond with it. Okay? Now, you all draw for me that Newman projection. We're going to draw that Newman projection. And we'll look at it the correct way. Right? You're going to want to have the carbon with the white in front because that's how I'm holding it. So you're looking down this bond. The carbon with the red is going to be behind. Where do we start? We're going to start with the back carbon, right? Okay. I've got the red sphere going up, and I've got the two sticks coming down. Then I've got my front carbon, right? And kind of going over here is my white sphere. Going up there is a stick, and going over there is a stick. That is that Newman projection. So what have I done in going from here to here? I have simply rotated the molecule a little bit. Okay? And what you'll see is that these things start to get close together. This and this are starting to get closer together. They're further apart here, now they're closer. Do things want to be closer or further apart? Further apart. So what can we say about the stability of these two conformers? This is less stable than this one. Okay? And that's important. Molecules will try to adopt the lowest energy conformation. Okay? And you can do this in computers, you can build models in computers that can actually calculate these energies. That's beyond the scope of this course. Okay? That is called a Newman projection. And it's how we represent conformations. Conformational. Would the name of those two conformers change? No. It's still white sphere, red sphere, or actually red sphere, white sphere, ethane. Okay? But they are different in terms of their stability. This is less stable than this one. Okay? I can tell you that we are going through this at such a low level, you will not completely grasp that stability argument. And that's okay. But you will see it at play when you get to biochemistry. You will see that proteins will start to take on shapes in 3 dimensions because of different conformations of the amino acids. You will see that fatty acids will change their shape and get into an enzyme to be metabolized. And they can do that because they have single bonds that they can rotate around to fit into the active site of the enzyme. So you're going to learn about a lot of that kind of stuff. So it is important. Okay? So we just went through that whole exercise. Okay? But when you look at the energy, so here's an example of, what's that molecule's name? Upper left. I'm going to build it for you here. What's the name of that molecule? What's the name of that? How many carbons do I have? Do I have 5? I've got 4. 1, 2, 3, 4. So it's butane. So this is butane. So we are looking at butane. Which bond are we looking down? Are we looking down this bond, or this bond in that Newman projection? Let's call it bond 1, bond 2, or bond 3. Are we looking down bond 1, bond 2, or bond 3? If I'm looking down bond 1, that would be your Newman projection. Looking down this. Is that what you see? What do you see? You see that. Right? You see these two carbons. This one would be the dot. This one would be the circle. And you've got a methyl group up here and a methyl group there. Right? I'm trying to go away, actually. Right? That's what you're looking at. Okay. When you look down that carbon-carbon bond that we're calling bond 2, everything is staggered. Everything is as far apart away from each other as it possibly can be. And we call this anti. The two groups, the two methyl groups, are as far apart as they possibly can be. That's called the anti-conformation. Now we're going to rotate 60 degrees. Which carbon atom are they rotating in that first 60-degree rotation? The front one or the back one? They are rotating the back one. Very good. And they are rotating it clockwise or counterclockwise? Clockwise by 60 degrees. There it is. And mine wants to, there we go. This hydrogen and this methyl group are what we call eclipsing one another. Okay, they are very close to one another. What do you think happens to the energy from going from there to there? Does it go up or does it go down? Down is more stable. Up. So this is lowest energy. This is a little higher energy. Is a hydrogen big or small? Small. So it's a small thing with a big thing. Yeah, you know, but it's not too bad. Now let's rotate another 60 degrees. Now we have this. We call this gauche. G-A-U-C-H-E. But it's another staggered conformation. But it's gauche because these two big groups are now starting to get close to one another. Is that going to be higher in energy or lower in energy than that? Going to go down maybe a little bit, but it's starting to interact with this big thing, right? Now if I rotate another 60 degrees, what happens? I have another eclipsed, but now the eclipsing is occurring from these two big groups. What do you think the energy is going to happen there? It's going to go way high. It's going to be very unstable. And now we rotate another 60 degrees. That's another gauche. We rotate another 60 degrees. That's another eclipsed, right? And then we rotate another 60 degrees and we're back to our starting point. Okay? Usually on an exam, we talk about 60-degree rotations, approximately 60 degrees. Okay, so there, that's approximately 60, that's approximately 60, that's approximately 60, so on and so forth. But in reality, you have an infinite number of conformations, right? I can do that, 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 that. But these are pretty minor. But 60 degrees, pretty major. Okay? So, these are not all equal. So if you were to go and look at in the magic microscope, what do you think the conformation would be that you would see the most of? Which one of those? The staggered anti, number one. That's going to be what this molecule looks like 99.9% of the time, because it's the lowest in energy. Nature's lazy. Nature wants to be in the lowest energy conformation, lowest energy everything, all the time, okay? So that's what we're going to get with that particular molecule. All right, let's build. Let's add a couple more carbons. So I've got 4 carbons here. I'm going to take 2 more carbons, put them together and make hexane. And what I'm going to do now is I'm going to connect the 2 ends together and I'm going to have what? That's a ring. What is it? Cyclohexane. But when we draw cyclohexane on the board, we draw it flat, right? We just draw it as a flat ring. Build your model and try to make it flat. Try to make it flat. You made it flat. But what's kind of weird about it? You're starting to see bonds starting to pucker, right? Yeah. They're not straight anymore. You feel like it just doesn't really want to fit that way. And in fact, if I push on it just a little bit, it'll pop back into this structure. This is the structure that it likes to be in. This is called chair cyclohexane. Can anybody tell me why it's called chair? Yeah, this group comes up, this group goes down, and this looks like the seat. It looks like a lounge chair, right? There's my footrest, There's where I place my buttocks, and there's where I place my head, right? Sitting on the beach. This is called chair cyclohexane. It's the most stable form of cyclohexane. And when I look down each of these carbon-carbon bonds, I notice that the Newman projections are all staggered. And staggered's good, right? But what happens when I flatten it out? Notice how hard it is for me to flatten it to start with. Can I flatten it? Yes. But now when I've got it flat and I look down the carbon-carbon bonds, what do I see? Everything's eclipsed. Everything's starting to get in the way of everything else. So it would much rather sit like that. Okay? That is called chair cyclohexane. And what you're going to recognize, and I don't have enough pieces to do this all over, okay, but your model kit, or the projection up here, you will see that they put blue and they put white for the different types of hydrogen. Okay? Hydrogens that are going straight up, we call those axial. Imagine that there's an axis running through this, and those are parallel to that axis. These blue ones are called axial hydrogens. The ones that run around the equator are called equatorial. Are they the same kind of hydrogen? They are not. They are different. I can tell them apart. Some are going up, some are going around the equator. Okay? But magically, watch this, what happens when I take the footrest and I make it the headrest, and I take the headrest and I make it the footrest. They switch. This is called chair to chair interconversion. And guess what cyclohexane is doing all the time? It is interconverting because it has single bonds. It can rotate around these single bonds a little bit, and it can form one chair and another chair. This is called chair-to-chair interconversion. Okay? Is this chair more or less stable than that chair? They're the same. They're exactly the same. Now let's suppose I take one of these blue hydrogens off and I replace it with, let's just put a methyl group on it. And I'm going to put a couple of white spheres here. This is what happens when the model puts 10 years old. It gets worn out. There we go. Notice the axis. So this methyl group is in the axial position. Okay? Is this more stable or less stable than that? Is this, which one's more stable, this one or this one? You think up, methyl group up is more stable? Why do you think that?
Because it's farther apart from.
Is it? So these are the hydrogens that we're looking at. So if I look at that, right? Now if I flip it, which one's further? This one. Big groups are always going to want to be equatorial because they don't start to crowd other hydrogens. This is called 1,3 diaxial interactions. Don't worry too much about that name, but 1, 2, 3, 1, 2, 3. So we have this axial group, which is big, interacting with this axial hydrogens, and those are bad. So it's going to, if it was like this, it's going to flip and be like that most of the time, okay? In fact, quite a bit of the time, okay? So let's learn how to draw cyclohexane in its chair form. Drawing cyclohexane is the bane of a lot of students. And you all might be saying drawing a 6-membered thing like this isn't too bad, and you're right. But that doesn't give me any perspective. You need to know how to draw it as a chair. Okay? You typically start, at least I do, I typically start at the footrest and you make kind of a V that's a little lopsided. And then I draw in the seat and one of, oops. You try to make them as parallel as possible, making one a little longer than the other, and then you put in your headrest. Okay? You can actually download templates that you can trace if you want. It's perfectly fine. Okay? And then we can put in axial groups. Let me use different colors for this. So let's make the axial groups green. Right? So we've got our axial groups, and then we can put in our equatorial groups. We'll make those purple. There we go. This will take some practice. Okay? We are going through it very quickly today, but embrace the practice because it's very, very important. Okay?
I didn't get that.
I
Could you
did.
try again?
I could, but I won't. Even Siri's confused. Right. So what will I expect you to do on an exam? Am I going to expect you to draw stuff? Yes. Am I going to grade your drawings? No. But if you can't draw it, you won't be able to pick the right answer. I will give you space to work your answer, and you will be drawing things to try to determine. You'll be building a model. You'll be drawing things. It will be fair game for me to say which of these molecules is the most stable. And you would need to draw them. You need to build models of them. You need to do chair-to-chair interconversions. You need to try to figure out which one is the most stable. Okay? That's perfectly fair game. Okay? So we just talked about this so-called ring flipping or chair-to-chair interconversion. I'm not going to go over it anymore. Okay? Here's the example we just did. Right? Where we have the methyl cyclohexane. And mine is all bending, all terrible. Right? So there it is. Right? Notice what the magic microscope gives us. 95% of it is like that. Only 5% of it is where the methyl group is axial. If I go upstairs right now and I get my bottle of methyl cyclohexane out of my cabinet and I go run what's called an NMR, again we'll learn more about that later, I would find that about 5% of the cyclohexane is like this and 95% of it is like that. I can see it in that experiment, okay? What do you think is going to happen as this group gets bigger and bigger? What if I put an isopropyl group here? What do you think would happen? Do you think it'd still be 95 and 5? What do you think it'd be? Yeah, I mean, essentially, if I went and ran the experiment, all I would see is that. I wouldn't see any of the other, or I wouldn't be able to detect it very easily, okay? So the bigger the group, the more it's going to want to be equatorial and not axial. Okay, that's the take-home message. The bigger the group, the more of that it's going to be in the equatorial position. And why is that? Why does the big group want to be equatorial? To get away from the other stuff. That's right. It wants to get away from those hydrogens on the number 3 position, or whatever groups are there. You want to minimize those positions, all right? So we're going to finish up today by playing with some models for a little bit before we have our quiz. I want you all to get in your groups, get your models together, and I want you to build a model of 1,2 dimethyl cyclohexane. Now, For your exams, you're all probably thinking, do I have to really put all the methyl groups on? You can use spheres, that's what they're for. So imagine that we're just going to use the white spheres to represent methyl groups. Okay? So go ahead and build a model of 1,2-dimethyl cyclohexane. Put it in a chair conformation to where one of the methyl groups is on the headrest. Let's start with that. So I'm going to put a white sphere on carbon number 1, and I'm going to put a white sphere on carbon number 2 somewhere on carbon number 2. I'm going to grab one of the, and I'm going to make that my number 1 carbon. I'm going to put my methyl group pointing up. Did we all build the same thing? Is yours the same as mine? What's different about it? They're both on carbons 1 and 2. They're both carbons 1 and 2. 1, 2, 1, 2. Or what's this? Huh? Well, it doesn't matter. Just think of them like that. Okay. This methyl is going up, so it's axial, right? Just like mine. What's this methyl doing? It's not going down, so it's equatorial, right? So you just built one where the methyl group is axial and equatorial, and both of mine are axial. Are these the same molecule? They are both 1,2-dimethyl cyclohexane, but they are not the same. They will have different physical properties. When you take, which one's yours? This one's yours. When you take yours and you flip it, notice you still have axial equatorial. Notice what happens when I flip mine. I now have equatorial. So which one of these is more stable, mine or yours? You have an axial group. I don't have any axial groups. Mine is more stable. So how do we distinguish this? Right? 1,2-dimethyl cyclohexane, we all built something different. Well, half of you built probably what I built, half of you built what she built. So how do we distinguish this? You can't say one up, one down. You can't say axial equatorial. That's not part of it. But imagine if I take the cyclohexane and I flatten mine. Now take the cyclohexane of yours and flatten the cyclohexane. Okay. What do you notice? Hold yours up so people can see it. So it's kind of flat. What's the difference? If I take this plane that are these 6 carbons, my methyl groups are on opposite sides of the plane, right? Hers are on the same side. Okay? We have a way of naming this. When groups are on opposite sides of the plane, we call that trans. This is trans-1,2-dimethyl cyclohexane. Okay? What I built was trans 1,2-dimethyl cyclohexane. What do you think she built? What's another word that goes with trans? There's trans and there's cis. Okay, and you built the cis version. Cis is on the same side of the plane. So when I look at hers, and try not to drink it. So there's the plane. The 2 methyl groups are on the same side of the plane. They're both on the top side. They can also both be on the bottom side. It doesn't matter. All I have to do is flip it. But they're both on the same side of the plane. This would be cis.
I'm not sure I understand.
Yeah. 1,2-dimethyl cyclohexane. Okay? And we just made an argument that the trans is more stable. Why? Obviously, it's not in this conformation because both things are axial. But when I ring flip it, both things are equatorial. When you ring flip yours, you always have something axial. So mine's more stable. Does that mean that trans is always more stable than cis? No. Move one of your groups over to the number 3 carbon. Just move it from 2 to 3. Now make your argument. And in this case, I made, if I flatten it out, I made trans 1,3-dimethyl cyclohexane. And when I look at it, no matter what I do, I'm going to have one that's axial. But it's still trans. That is trans 1,3-dimethyl cyclohexane. The two groups, when you think about it being flat, on opposite sides of that plane. Now, if I made cis, sorry about this. Get on there. All right, now if I flatten that out, right, those two hydrogen, or those two methyl groups are on the same side of the plane, but notice what happens, right? There they're both trans, but if I ring flip it, they're both equatorial. So trans 1,2 disubstituted cyclohexanes are more stable than cis, but cis 1,3 disubstituted cyclohexanes are more stable than trans. And how in the world are you going to figure that out on an exam? You're going to build a model. Do not try to memorize this. The only thing you need to memorize is, wait a second, I know what cis and trans mean, either on the same side of the plane or on opposite sides, and I know that I want to have my big groups equatorial if at all possible. You can figure it out just by building some models. Okay?
How would you draw that?
How would I draw this?
Yeah.
So, there are a couple of ways that we can draw it. We're not technically to that point yet.
Oh, never mind then.
Never mind then?
Yeah.
Okay. So we'll cover that later. I want to answer questions. Does that make sense? It's not completely supposed to yet. But if you're getting an inkling of it, then you're on the right track. But you have to build a model. If you try to do this in your head, and if you try to memorize, if it's 1,2 and it's cis, and if it's 1,2 and it's trans, if it's 1,3 and if it's 1,4, you're just filling your head full of stuff that is going to confuse you. Build the model, and all you need to know is you want your big groups to always be equatorial. Okay? So, let's build some more models. Build a model of cyclohexane. 1-methyl cyclopentane, or methyl cyclopentane. Why did I correct myself? Do I need the number? It's always number 1, right? What can you tell me about the cyclopentane? How does that model feel?
More rigid.
Pardon?
More rigid.
More rigid. The rotation around these bonds is not quite like what we were seeing with cyclohexane. I had trouble, my cyclohexane wanted to fall, right, because it was so easy to rotate. This is a little more rigid, right? Can I make a headrest and a chair rest? No, it's gonna take on a little different shape. It actually seems okay to be all in a plane. But all of these things start to eclipse each other. So really one of these groups will kick out and kind of twist. It forms kind of a twist to where it sort of makes all of these things staggered a little bit. Okay? What happens if we remove a carbon and now we make cyclo what? What would 4 carbons be? Cyclobutane. Is it more rigid or less rigid than cyclopentane? More rigid, yeah. It is definitely more rigid. And it will twist. It won't, we don't want things to be planar if at all possible, but it will twist. Okay? But I still don't have as much play in this as I had in the cyclohexane. And so things, if you look at the Newman projections, things are really pretty close, even when you twist it. You don't get that completely staggered Newman projection. Now, you have a special piece in your model kit that is a little more of a silvery gray color. And it's really kind of flexible. Okay? You need it when you go below 4 carbons. So let's remove a carbon. And now we make cyclo what? Cyclopropane. What can you tell me about cyclopropane? You can see why I needed the other piece. What can you tell me about those bonds? Are they stable or unstable? Or unstable. Why?
I found this on web.
Why? You're right. But why? What is that? What makes you feel that way?
They look resistant, like they don't have the bonds or
It looked angry.
They look angry?
Period.
And what were you saying?
Resistant, like they don't want to stay,
That's right. They're kind of trying to get away, right? They're trying to pucker out, right? That's exactly right. Some chemists call these banana bonds because they kind of look like a banana shape. Okay? But nonetheless, cyclopropane is a molecule that you can make. This is what I did my PhD on, making these molecules, at least in part. Okay? You will find these molecules. We used to use cyclopropane as an anesthetic. People would go in for surgery and we'd gas them with cyclopropane. They would go into anesthesia and we would do whatever we needed to do. We stopped doing that, I think, largely because it's highly flammable. And when you were having heart surgery and they stop your heart, they have to start it again with a shock. And people would catch on fire. It happened. Not a lot, but it did happen. Okay? But that's cyclopropane. You can make it, but it's under a lot of stress and strain. It's the smallest possible cyclic molecule that you can make. And what you'll notice, if you remember back to your high school geometry, 3 points always define a plane. This must be, all atoms must be in this plane, or all carbon atoms. You can't flip. And so what does that tell you about the things? When we look at the Newman projections, they're all eclipsed. So the smaller we get in ring size, the more and more the bonds get rigid and the more and more they get eclipsed. So is this more stable or less stable than cyclohexane? It is less stable. Okay? It is less stable, which means it is higher in energy. In fact, you can burn cyclopropane and get more energy per carbon atom than you can out of burning cyclohexane because it's higher in energy. Okay? It holds a lot more energy in it than the cyclohexane does. So which of the rings, 6, 5, 4, or 3, do you think is the most stable? 6. And when you all start going into biochemistry, you're going to see, when you start talking about hormones, you're going to see a lot of things with 6-membered rings. A few things with 5-membered rings. But you won't find a lot of 4-membered rings and 3-membered rings in nature. They do exist, but they're rarer. And it's because the 6-membered ring, or cyclohexane, is the most stable single ring system that we can have. If you go 7, 8, 9, it starts to get less stable again. Yes?
Is that
so that is a stable ring system. Because everything is staggered. Things are as far apart as you can get them. And as you start to remove carbons or other atoms and make smaller rings, things start to get closer together, bonds start to get more rigid, and things start to get in the way. Folks, you're going to have to build models. I can't say it enough. I'm saying it a lot because you need to do it. You need to do it when you're working on your homework problems. I would do it while you're trying to name molecules, even if they're straight chain, if you have enough carbon atoms to do it. It'll help you. This is your accounting system. If you put the carbons together correctly, you'll be in good shape. Okay? We will continue to play with our model kits as time goes on. I think you all have a lab too that where you're going to be working with your model kits. So some different types of exercises that you can do there. All right. I'm going to give you a few minutes back of your life today. So I need you to turn in problem 2.18. Again, put your name, print your name please on your front page and put your ID number and turn it in at that desk that has nobody sitting at it right next to the door. And I will see you all next week.